So the discussion we had last time was the transistor is obviously a 4-terminal device. The gate, drain, source and body, and you have capacitances almost across all the terminals, right. This is CGD, CGS, then you have the CDB, CSB, and you also have one capacitance going across like this, and this is CGB. Okay. So we said that the CG total gate capacitance, right, gate cap is basically what? Just C naught, right, which was epsilon ox WL by T ox plus what is it? C naught into C ox into L overlap into W. 2 times. Perfect. Okay. So now I just left the expression here, but remember that this L overlap is basically a constant for a given technology, right. Once you do the annealing and all that, this L overlap actually is reasonably fixed. It goes in by the same amount and therefore it can be absorbed as a technology constant, right. So therefore what you do is you basically say that this is C naught plus 2C overlap into W, okay, and this can be further written as C ox into WL plus 2C overlap into W, okay. Now it doesn't matter whether you are going to treat this 2C overlap as a technology constant or C overlap as a constant, okay, it's just that may be a convention, okay. So the point is I can write this as C ox into WL, C ox into L plus 2C overlap into W. So basically I am bringing out the design parameter and the technology constant separately, right, and both these capacitances scale with W. That is the main conclusion that we will come to, right. If W increases implies CG also increases. As a designer, this is what you should really know, okay. Just to be careful, remember that the units of this C ox will be in femtofarad per micrometer square. It's a capacitance per unit area, whereas this guy has to be femtofarad per micrometer. It's a capacitance per unit length, okay. So per micrometer, just keep this in mind, okay. Dimensionally, if you understand the dimensions of these constants, you can easily actually predict what the actual capacitance must be. You must just multiply by either area or by some length, that's all, okay. So we were discussing the diffusion caps. So we said that if you have a PN junction, P, then you have some depletion region, right. The concentration is Na here of the acceptor impurities, donors concentration is Nd, right. Then just to refresh your memory, what is the whole concentration at this edge here? Na, right. So this is Na. What is the whole concentration here? Ni squared by Nd, right? So Ni squared by Nd, which is what? This is hole concentration. Okay. So therefore there must be a potential drop across these two, right? So you can find out what that drop is as phi naught is equal to Kt by Q ln of Na Nd by Ni square. Just like we did for the CMOS transistor, you can calculate what this difference is. Okay. Now this, because there is a depletion capacitance here, okay, if you look at this, there is a depletion capacitance here. When the hole goes, you get negative immobile carriers here, right, and this is plus, you have an electric field from the N to the P region, and that itself is like a capacitance now, okay. And if you increase the reverse bias, then this depletion region goes up, and therefore the capacitance will drop. Okay, so you don't have to remember any of these expressions that I'm going to show you on the slides now. You will be given those expressions, or they will all be evaluated as technology constants. You should just know where these numbers are coming from. Okay, so it turns out that the capacitance per unit area, okay, is as shown here. Let me just, maybe I can just write it down. Capacitance per unit area, okay, is equal to Cj naught, okay, is what? Root of epsilon silicon Q by 2 into what? Into Na Nd by Na plus Nd into 1 over phi naught, okay, and phi naught is the expression as given here, right? So using this, we now have to go back and find out what the diffusion capacitance components are in the transistor, okay. So how this gets affected by the bias, I will tell you later when we put down the picture of the transistor. But effectively, we have a Cj0, which is a capacitance per unit area, and if this has a width like this, right, and it has an area, right, so what happens is, there is basically, let's say this is my L, okay, and this is my W. Then what is the net capacitance out there of PN junction? Cj0 into W into L. This is what you must keep in mind, okay. So now the complication in the transistor is not really the formulae. It is just imagining and visualizing where these diffusions are, okay, because we are basically looking at it in a 2D plane, but the transistor is actually a 3D picture. So to get that, I will try to illustrate it with some figures here, and with that you should be able to easily calculate what the net capacitance is, okay. So I'll go back to some engineering drawing things where I look at the top view and the front view, okay. With that we should be able to construct this is the front view of the transistor. I have my gate, oxide, and my diffusion. Why does the diffusion go inside? Because of annealing, right? That's what gives rise to the overlap, okay, N plus. So let's assume that this width is xj, okay, and this spread here is Ls. Okay, so remember this small delta here is what? L overlap, and the channel length effectively has now come down. It is going to be between these 2 points. Okay, so in fact if you go back to the expression of the gate capacitance that we wrote, you might now ask, why is this not just, you know, if I remove this from where? From here. Okay, I can write this expression as C aux into W L plus 2L overlap, right? So you might think that, well, this is effectively the same channel length, right? But there is a difference, because this channel length that we are showing here is what is known as the drawn channel length. Means this is the intended channel length that we wanted, but because of diffusion and all, it reduces. So when I say L, it means the same L that appears in your current equation, mu n C aux W by L. It's not mu n C aux W by LD. That L that we talk about is always what appears in your current equation. Okay, and that's why I'm not writing this capacitance as just some LD. I'm writing it in terms of WL and the overlap lengths. I'm not combining them and writing it as LD. Okay, yeah. So now, how does the top view of this transistor look like? Okay, this is my top view. I'm going to like just extend this. Okay, this is my top view. Okay, obviously here is where I have my gate. Okay, this is my oxide. First, tell me what this dimension is. If this is the top view. Yeah, W. Great. Okay. Now, clearly you can see that these two regions to the left and right of the gate oxide are my N plus regions. Okay. And there is now going to be a depletion region that forms around, all around it. Right. So, if you look at this, if you look at the diffusion region here, let me draw it in magenta, it will be like this, right? I am now going to map that diffusion region on top. Okay. So what do I do? If you look at this, let me just take that up further. Right. Right, and then I have a depletion region around it like this. You agree? This is the N plus. Right, similarly here also I have something like that, N plus. Now where is the depletion region under the on the other side, on the fourth side? For both drain and source, I have shown the depletion region only on 3 sides. Right, this is like a rectangle. So where is the depletion region on the fourth side? Yeah, under the channel. So that picture is not so straightforward, because what happens is, now when I apply my gate voltage, that depletion region just seamlessly merges with the depletion region under the channel. So therefore we don't consider that fourth side when we are taking into account the calculations for capacitance here. That fourth side is basically accounted for under the gate. Okay, because we have already considered the gate capacitance and other things already there. So we don't want to double count that here. This is just one convention, by the way. Okay, I am just giving you the rationale behind this kind of a convention. Clear? Okay, so now this is a PN junction and I have a between the N plus and the P, I have a capacitance per unit area called Cj. Okay, capacitance per unit area. Now all we have to do is find out what all the area components are, right? So where is the, if you look at this front view, you agree that there is going to be one diffusion capacitance. Now let's assume that this is a rectangle, proper rectangle. Okay, I am not worried about all the deformations, we can correct for that later, okay, through some empirical correction. So this is a rectangle, this length is how much? Ls. And then we have a depletion region like this. So what is the area under this region? So if you look at the top view, I am asking, there is a bottom plate, the bottom N plus region which is in contact with the P. I want to know what the area of that region is. Yeah? How much? No, I can't hear. W? W into Ls, that's the area. Now will you have a top plate component? No, because the diffusion implant is happening like this, so the diffusion N plus happens till the top. There is no P region after that. Okay, the N plus cuts off abruptly here. Therefore, there is no top plate. You have only a bottom plate capacitance. Okay. So how much is the bottom wall capacitance? C bottom is Cj into how much? W into Ls. Okay. Yeah. Huh? Ls. What is Ls? Ls is basically the how much of diffusion I have here. You look at this. The N plus width is what I am calling, not width. Since this is the width, the other dimension of the N plus region is Ls. Okay. Now that is just one component. Now there is also the perimeter capacitance which I need to consider, right? So what are the perimeter components I need to consider? I need to consider these components, right? Because I have accounted for the bottom plate already here. So what is my perimeter capacitance? Or rather, it is called side wall capacitance for obvious reasons. Okay, and this is called bottom plate cap or bottom wall, doesn't matter. Okay. So side wall cap is again going to be Cj. Okay, side wall, C side wall is, exactly, it's going to be Xj into what? W plus 2Ls, right? Because this dimension is Ls and this other dimension is W. Total perimeter we are talking about is W plus 2Ls. So it is Cj into Xj into W plus 2Ls. Okay. Now Xj is also a technology constant, right? Therefore, what do? I am simply going to write this as Cjsw, side wall, okay, into W plus 2Ls. Okay. Both these components are not dependent on the channel length, quite evidently, because that dimension does not even come into the picture here. Channel length is under the channel. Okay, it only depends on the width. Okay, so again we are going to do the same trick. We are going to split this as technology constant multiplied with some design parameter. Design parameter here is what? Only W. L is not available here, even for analog guys, right? So the CDB is basically C bottom plus C sidewall. And of course, this is also equal to CSB if the biases are the same, right? So CSB equal to this. So how much is that? It is CJ into WLS plus CJSW into W plus 2LS. Now, why didn't they combine CJ into LS? LS also is fixed, right? Why didn't they combine CJ into LS as a technology constant? See, what is the idea of making it a technology constant? If I give you that one number, you don't need any more information, right? Now, if I give you CJSW, I don't need to give you XJ. For whatever reason, you don't need XJ, right? In this model, I just need to give you that one number and I am done. I multiply it by W plus 2LS, I'll get the answer. Now, if I give you CJ into LS as one number, do I need to give you LS? Yes. Why? Because I need it for the perimeter capacitance. Therefore, this you just leave it as a capacitance per unit area and multiply it by LS. Okay. So the total capacitance CSB equal to CDB is equal to CJ into WLS, okay, plus CJSW into W plus 2LS. Yeah. No, my question I asked you is, like I combined this into CJSW, why can't I combine CJ into LS and give you one number? Say that also I will make it a capacitance, because now look at what is happening. This guy is femtofarad per micrometer square, capacitance per unit area. This guy is femtofarad per micrometer. What I am asking you is, why do I have to worry about that? Why didn't I make this also? Because LS is also fixed for a technology, doesn't change with W or nothing. Okay, so why can't I just give you that as one number? The point is, you need LS in order to calculate the other capacitance, perimeter capacitance, sidewall capacitance, and therefore I have to give you that number. So it doesn't make sense to combine those two as one constant. That's all. Okay. So this is the total capacitance and the origin of all the capacitance components that we have, right? Again, the most important thing is to see is whether it is CSB, CDB or the gate capacitance, every capacitance scales with W. Okay, this also I can write as W into CJLS plus CJSW into 1 plus 2LS by W. Okay, if you leave out that 2LS by W, if W's are large, right, then typically to a first order everything just scales with W, or that's effectively like a bias term, right? It's Y equal to mx plus C. That's the C of the equation. W is basically the slope of the equation that we are talking about. Okay, so as a designer, this is what you need to know. If I scale W, all the capacitances will scale linearly to a first order, right? So if you tell me that I will just make the size of the transistor much bigger, then be aware that you are going to actually load the previous guy significantly more. On the other hand, if you increase W, like we discussed in last class, the resistance drops. R equivalent is proportional to 1 over W. The resistance drops, there is no doubt about it. So this fight between resistance and capacitance is what is going to dominate your delay, and there is therefore going to be a sweet spot somewhere. You can optimize your circuit to get minimum delay, because if I increase W, resistance is coming down but capacitance is going up. Of course, if I multiply these two components, it seems to cancel out, which is true. What is known as parasitic delay of a transistor is to a first order is independent of W. Parasitic delay is due to its own capacitances. Whatever I showed you now are the transistor's own capacitance. It's not any load capacitance. So they are called parasitic capacitances. So parasitic delay is to a first order independent of W, right? But of course, because I have a load guy coming in, it brings in some very interesting optimizations that I can do. We will look at all of that later on in this course. Just the final thing, how does this Cj scale with the applied potential? Okay, so if I apply VSB, right, then this basically becomes Cj into 1 by 1 VSB by phi naught, where phi naught is as given here, power m, and m is typically 0.5. Okay, this again is an empirical fit, and you don't need to remember this equation. Just remember that if I reverse bias with a higher voltage, the capacitance drops. Okay,